Okay, so section 6.8 is about the measurement of the angular momentum. And as you very well know, there are three components of angular momentum. So px, py, So this is the linear angular momentum notation. So Lx, Ly, Lg. So L is the notation for, or the symbol for angular momentum. And we have three different components, Lx, Ly, and Lg. So the keyword is that precise value of this angular momentum cannot be measured simultaneously. So this somewhat reminds you of the Heisenberg uncertainty principle for the position x and the linear momentum px, right? So we are going to discuss that. So first we are going to figure out the explicit expression of this angular momentum. So for angular momentum in the x direction, that is given as the Lx, and we want a operator for the Lx quantity. So the angular momentum operator for the x-axis will be denoted as Lx hat, and this is defined like y multiplied by pg minus g py. So angular momentum Lx operator is defined with the linear momentum pg and py with some scalar multiply y and g. So we have to figure out the explicit expression of the linear momentum px. So this is given as minus I h bar ddx. Or if you want to handle three-dimensional system, that means there are three independent variables. So you might want to say partial differential notation rather than ordinary differential notation. So in the same way, you can define py, pg operator. So with this expression, you can write the explicit notation expression for Lx operator. So y lambda g minus g lambda y. So both pg operator and py operator, both of them will have the common factor minus I h bar. So you can factor this constant out. And similarly, you can write down Ly. So this will be gpx minus xpg. And Lg operator is also similarly defined, xpy and ypx. So these three expressions are the explicit expression for three components of angular momentum. And so now we are dealing with the rigid rotator. And for the rigid rotator description, the spherical coordinate is better option than the Cartesian coordinate, spherical coordinates. But as you can see above, all the angular momentums are defined in terms of the Cartesian coordinate. So what we want and what we have to do is transform the angular momentum expression from the Cartesian coordinate to spherical coordinates. So we already have some practice for similar thing. So when we transform the Legendre polynomial equation, like they are given as the zeta function, but we want the expression in terms of the independent variable x. So you can do that, you can follow the similar logic, and that will give you the 3 operator in terms of the spherical coordinates, minus IH bar, minus sine P, round zeta, cotangent zeta, cosine P, round P, and minus IH bar, sine P, cotangent zeta, sine P, round P. The final expression is minus IH bar, round P. So from this relation, we are going to figure out the eigenfunction of each operator. So first, what we already know is the P dependence of the spherical harmonics occurs in the factor, this function, right? Actually, this is the P part of the spherical harmonics. Maybe you want to add subscript m here to explicitly denote the magnetic quantum number. So which operator, 3 of these operators, which operator will have the eigenfunction exponential IMP? Which operator? As you may realize, the first 2 operator cannot have the eigenfunction like this one, right? So the way you can identify the eigenfunction is you can just apply the operator on that function, and to check that if the final result is given as the some constant multiplied by the original function. But unfortunately, neither Lx operator nor Ly operator satisfy this function, satisfy this relation. But what about the Lg? This one. So let's apply Lg operator on P part of the spherical harmonics. Then the explicit expression for the Lg operator is minus IH bar, round P. So when you differentiate the exponential IMP in terms with respect to P, then you will have minus IH bar, IM, and exponential IMP. So if you multiply these two numbers, then you will have mh bar exponential imp. So if you apply the LG operator on exponential imp, the final result is mh bar multiplied by exponential imp. So it is exactly eigenproblem format, right? When you apply the operator on the function, the final result is constant multiply the function. So in that case, we say that LG operator has the eigenfunction of exponential imp. So this is the eigenfunction. And mh bar, this is the eigenvalues of LG operator. Okay, so whenever you measure the angular momentum on the g direction, you always have the mh bar. The integral multiplies of h bar, right? So because the m is restricted to 0, plus minus 1, plus minus 2, etc. Okay. But however, the spherical harmonics are not the eigenfunction of Lx and Ly. So this can be easily verified. So let's say we want to check that spherical harmonics y1 minus 1. This is not an eigenfunction of Lx. So if you want to show that some function is not an eigenfunction of a specific operator, you can just apply that operator on that function. So y1 minus 1 means the L value should be 1 and m value should be minus 1. So let's explicitly express Lx and y1 minus 1. So Lx is given as the Lx is given as minus ih bar minus sine p round theta minus cotangent theta cosine p round p. So this is the expression for Lx. And spherical harmonics with L equal 1 and m equal minus 1 is given as square root of 3 over 8 sine theta exponential minus ip. So you can perform the partial derivation with respect to theta here and p here. So when you differentiate the spherical harmonics with respect to theta, then you can keep the p value as constant. And similarly, when you differentiate the spherical harmonics with respect to p function, then you can take the theta value as constant. So it requires some calculation, and the final result would look like h bar square root of 3 over 8 pi cosine theta. So this is when you examine the format of this equation. So you apply the Lx on y1 minus 1. And the final result is this is nothing associated with the y1 minus 1 function. Their form is totally different, right? So this is the y1 minus 1, so yellow box. But the final result doesn't really have anything with the spherical harmonics, y1 minus 1. So y1 minus 1 is not the eigenfunction of Lx operator. Okay? So that means if you want to measure the Lx value of the y1 minus 1 function, the result is different time to time. So whenever you measure the Lx angular momentum x direction, you will have different result because there is no definite value for this function. But still you can calculate the expectation value. So even though if we go back to the particle in a box problem, even though the position operator, it doesn't have the eigenfunction like so this is the eigenfunction for Schrödinger equation. Even though the operator x doesn't have the eigenfunction form like this one, but you can still calculate the expectation value of position x for this function, right? So no matter your function is the eigenfunction of your operator or not, you can still calculate the expectation value. So if you want to calculate the expectation value, then it is just like y1 minus 1 of complex conjugate and Lx operator and y1 minus 1 sine theta dp theta. So you can perform this integration and the final result will be 0. So the physical interpretation of the angular momentum expectation value is 0. That means the angular momentum is randomly oriented for the x direction. Okay. And let's talk about LG operator more. So we know that the spherical harmonics YLM, this is the eigenfunction of L square, the square of the total angular momentum, right? So I think you might remember that. So Hamiltonian operator H hat, this is the L square divided by 2I, right? So spherical harmonics, they are the eigenfunction of the Hamiltonian operator. So spherical harmonics can be an eigenfunction for any operator which differ by constant term. So L square operator is differ from the Hamiltonian operator by the constant vector 2i. So they can be the eigenfunction for L square. And eigenvalue is h bar square L plus 1. And we already discussed that the spherical harmonics is also an eigenfunction of LG operator, right? So if you want to explicitly confirm that YLM is the eigenfunction of LG, and this spherical harmonics can be explicitly given as NLM, the normalization constant, multiplied by associated Legendre polynomial and exponential function. So this is set top part and this is P part. So the explicit expression for LG operator is minus I h bar lambda P. So for this operator, the normalization constant and the associated Legendre polynomial, they can be considered as the constant. They don't have any part involving P function, P variable. So they can be taken out. NLM, PLM, LG, exponential IMP, right? So as we discussed, this will give you the MH bar, so MH bar, and now we have NLM, PLM, exponential IMP. So we recover the spherical harmonics YLM, MH bar, YLM. So spherical harmonics is also an eigenfunction of LG operator with eigenvalue MH bar, right? So if you remember it is not actually a theorem. If you remember some relation that if there are two operators, LG and L square, if they share the same eigenfunction, their commutator should be 0, which means the total angular momentum L and the angular momentum of the G component, they can be simultaneously measured because their commutator is 0. So the order of which one measure first, LG or L, total angular momentum L, doesn't really matter for this case. Okay, but if you check like Lx and L square, and their commutator is not 0, that means they don't share the same eigenfunction set. No common eigenfunction. And this means that they cannot be measured simultaneously. So it is very similar with the position x and px. So the commutator for these two operators is not 0. So they cannot be measured simultaneously. So when the two operators do not commute, it is very important to measure which one first. Okay, now let's move on to the next page. And now I want to talk about restriction on magnetic quantum number m. So far we just assume that the m value should be 0, plus minus 1, plus minus 2. But we haven't explicitly shown that why the m value should be like this. So this is just a assumption, right? So we are going to prove that here. So let's start the eigenvalue problem for operator LG. So as I mentioned, operator LG has the eigenfunction YLM, it's the spherical harmonics, and their eigenvalue is mh bar. So you are going to apply LG operator once more. So let's leave some blank here. So we are going to apply LG operator again. So in that case, LG square YLM, the left hand side. So for the right hand side, so mh bar is just constant, so they can come out of the operator. And operator will be directly applied on YLM. And the result will be we have another mh bar. So m square h bar square YLM. So this is our first expression. And we know that L square also has the eigenfunction YLM. And what is the eigenvalue of L square for YLM function? So it is h bar square LL plus 1, right? So this is our second expression. So now we want to subtract the second equation from the first equation. So L square minus LG square YLM should be equal to h bar square L plus 1 minus m square YLM. So what is the result of L square minus LG square? So L square, so you don't really have to focus on this is operator or just the scalar quantity. So let's just focus on the square of the angular momentum. So square of the total angular momentum, this can be expressed like the square over the Lx, square over the Ly, and square over the Lg. So if you subtract the L square from Lg square, that means this one should be Lx square plus Ly square, right? And Lx and Ly, this is the physical quantity, right? The angular momentum in terms of the x direction and y direction. So they are the real measurement, which means they should be real number. They should correspond to the real number. And the square of the, if you add up two real number, the square of the real number, and this should be some positive number, right? So let's reiterate. So Lx should correspond to the angular momentum of x direction. So this is physical quantity, right? So we don't know the exact value of this function, but anyway, this is physical quantity and you can measure this, which means this should be real number. And similar story for Ly. So if you add up the square of two real number, and this should be larger or equal to 0, right? So this value should be equal or at least larger than 0 or at least equal to 0. So L multiplied by L plus 1 should be large or equal to m square. So from this inequality, we can derive that the absolute value of m should be smaller or equal to L, with the restriction that m is the integer number. So that's why we have some very weird restriction. So m value should be larger or equal to minus L, or smaller or equal to plus L. Okay. So this tells us that we understand the two quantum numbers among four quantum numbers, right? So for atomic orbiter, the electron in the atomic orbiter, we have four quantum number, NL, MS. Now we understand why L should be larger or equal to 0, and why M should have such relation. But still, we don't know about the N. This will be discussed in chapter 7 in the hydrogen atom model. And we don't know the upper bound of the L value. So this one should be discussed in the chapter 7 too. But now we have some knowledge on the quantum number restriction, this red text. Okay, now let's discuss more about the angular momentum. This will be last topic of today's course. So let's take an example with L equal 1 case. So for the spherical harmonics with L equal 1, which m values are allowed? -1, 0, +1, right? And we know that L is related to total angular momentum. And what about M? M is angular momentum of g direction, right? So square of the total angular momentum is given as h bar square L plus 1 . So this is the square of the angular momentum, total angular momentum. So total angular momentum should correspond to h bar square root of L plus 1. So for this case, L equal 1, total angular momentum should be square root 2 h bar. And what about the angular momentum of g direction? So we can figure out by applying LG operator on YLM, MH bar YLM. So LG operator have the eigenvalue MH bar. So there are 3 possible cases of having total angular momentum as square root 2 h bar. The first case is g direction as a h bar, or 0, or minus h bar. So let's draw this on the 3-dimensional space. X, Y, Z. So total angular momentum is like the length of the vector. So this is like sphere, 3-dimensional sphere with the radius of square root 2 h bar. So this is L. So let's take the absolute value here. But the g direction, the angular momentum of the g direction cannot have any arbitrary value. So it should be plus h bar, or 0, or minus h bar. Right? So even though if we just consider the total angular momentum, the total angular momentum can span like 3-dimensional space with radius of square root 2 h bar. But due to the restriction of the available or allowed g angular momentum, so this looks like cone. So on this So this red filled area, that should be circle. So angular momentum can have the value on this cone, or angular momentum can have the value on this area, or another possible case is this area. So that means we have some restriction of radius, and we have some allowed g value. So that restricts our available space in terms of the angular momentum. So first layer corresponds to plus h bar. The second layer corresponds to 0 g direction angular momentum, and the bottom layer corresponds to minus h bar g angular momentum. Then what about the Lx and Ly? Do you remember that we cannot determine the Lx and Ly simultaneously, right? Lx and Ly, their commutator is not 0, so they cannot be determined simultaneously. So that's why we have some circle here. So if we project the first layer, this circle on the xy plane, so can you determine the radius of this circle? Top layers circles radii. That should be h bar, right? Due to the Pythagoras triangle, right? Because this is fixed as h bar, and the radius of the sphere is fixed as square root h bar. So that means the circle radius, this one, should be h bar. Something like this. So as I mentioned, all the values on this sphere, all the values on this peripheral, these are the combination of possible Lx and Ly. So it is possible like all the angular momentum is assigned to the x direction and there is no angular momentum for y direction. And it is also possible to share the angular momentum evenly for the x and y direction, something like this. So that means there are many possible combinations of Lx and Ly to satisfy this relation, right? The only constriction is Lx and Ly square should be h bar. So this is another example of why, this is another way to show that why we cannot determine Lx and Ly simultaneously, because there are many possible combinations for Lx and Ly. So I want to leave this as an homework for you. So we can determine the square of the total angular momentum and one of the angular momentum component. Like, even though we say that we can determine both L square and LG simultaneously, but actually in natural there is no G-axis like that, right? G-axis is our just convenience. We just label, okay, this is the G-axis. But so in nature there is no G-axis, so that means we can arbitrarily set G-axis. So all this commutator should be 0. So please practice by yourself. So it is problem 641. And another example, another thing that we have to check is Lx and Ly commutator. So we say that we cannot determine the remaining two angular momentum, and we take the example as the x and y direction. But actually, in nature, there is no x and y axis, so they all non-zero. So actually, they have some specific values, something like this. So the commutator of Lx and Ly operator is IH bar, LG operator. So I think this is also introduced in somewhere in. So you can use the. I guess you already practiced this one. So for your midterm exam. So I think you can practice by yourself. Okay, so this is the end of the chapter 6, and homework is, there will be a lot of homework. So I just finished evaluating your midterm, and so I'm going to change a little bit of my exam style.